Hello everyone. Let us have a glance over the problems based on divergence. Using divergence theorem, let us evaluate the surface integral of A dot ds, where A is 2xy plus y squared ay plus 4yz az, and the surface is the surface of a cube bounded by x is equal to 0, x is equal to 1, y is equal to 0, y is equal to 1, z is equal to 0, z is equal to 1. So let us look into the solution of the problem. The vector field is given by 2xy ax plus y squared ay plus 4yz az. Using divergence theorem, if you analyze the possibilities for obtaining surface integral of A dot ds, volume integral of del dot A into dv will appear. So del dot A, what is del dot A? Dou by dou x, dou by dou y, dou by dou z of dou by dou x of ax, dou by dou y of ay, dou by dou z of az. Because you know del is an operator, vector operator, which is defined as dou by dou x of ax, dou by dou y into ay plus dou by dou az, az, and vector A is assumed to have the components such as ax, ay plus az. So del dot A is specified as dou by dou x of ax, dou by dou y of ay plus dou by dou z of az. So in that case, surface integral of A dot ds is obtained from, according to divergence theorem, del dot A into dv. Okay, so what essentially we require is del dot A, and if you perform del dot A will be obtained from del dot A is equal to dou by dou x of ax. So that gives me 2y plus dou by dou y of ay. Again, that is also 2y. Similarly, if you look at dou by dou x, dou by dou z of az will also be equal to 4y. So that del dot A is equal to 8y. You know, A is actually 2xy, that's why I put 2y with respect to x if it is differentiated, and y squared ay, so it becomes 2y when it is differentiated with respect to y. The third component is 4yz. When it is differentiated with respect to z, it becomes 4y az. So del dot A is equal to 2y plus, right, this is 4yz, so 4y. You will see del dot A is equal to 8y. So when it becomes the volume integration of del dot A into dv, dv is replaced by dx, dy, dz according to the volume definition in Cartesian coordinate system. So you can find out that it becomes simply 8 into y squared dy, so y squared by 2, 0 to 1, and if it is an integration over x dx, it becomes x with lower limit is 0 and upper limit is 1, and with respect to z, when it is integrated, it becomes z with lower limit is 0 and upper limit is 1. So this becomes simply, what is it? It is equal to 8 into 1 by 2, which is equal to 4. This is how surface integral of A dot ds is computed as volume integral of del dot A dv. The next problem, verify divergence theorem. See, look at the statement. It is not like the previous one where you are asked to use divergence theorem to evaluate the surface integral of A dot ds. But in this case, you can find out that this is regarding verification of divergence theorem for a vector field d is equal to 3x squared ax plus 3 plus y z ay plus 3z minus x a z in the region bounded by a cylinder, a portion of a cylinder, which is specified as x squared plus y squared is equal to 9, and the planes x is equal to 0 is a plane which is cut through x is equal to 0 and y is equal to 0 is another plane which slices off the cylinder, and z is equal to 0, again it slices off at the bottom, and z is equal to 2, it slices it off at the top. So this becomes a shape of this kind, a cylinder, a portion of the cylinder. You can notice that, and this becomes completely a wedge portion cut because of running different planes such as z is equal to 0, z is equal to 1, and z is equal to 2, and y is equal to 0, and y is equal to 0, and y is equal to 1, y is equal to 0, y is equal to 0 and x is equal to 0. Okay, now what are all the surfaces available? How many faces are there? You can notice that there are 5 surfaces. One is at the top, the other one is at the bottom, the third one is right according to the notation, the left side surface, and you can see that the surface at the back side ds2, the surface at the curved portion ds3, the surface at the which is available at the top, the surface which is located at the bottom. So if you take all the surfaces, since the first surface is facing the left side, so ds1 is obtained from dx dz minus ay is the direction indicated by the vector perpendicular to the plane. Okay, ds2, where is it situated? It is at the back side, which we cannot view. So ds2 is actually dy dz multiplied by the unit vector indicating the direction perpendicular to the plane, so minus ax. And ds3, it is over this curved portion, r d phi dz, and you know that this is available in the direction perpendicular to the plane will be indicated by ar. ds3, ds4, where is ds4? ds4 is at the top. ds4 is equal to r d phi and dr r dr d phi. The positive z axis only, the vector is available situated vector perpendicular to the plane. Okay, and ds5 is of course available at the bottom of the cylinder. That is also could not be viewed by us. It is r d phi dz minus az. r d phi dz, the direction is indicated by minus az. So all these 5 surfaces may be useful in evaluating this integration. So with respect to surface 1, if I evaluate d dot ds, it becomes surface integral of z is equal to 0 to 2, first surface towards the left side. Okay, towards the left side, z is equal to 0 to 2, x is equal to 0 to 3, minus of, yes, it is minus of 3y plus z, right. The surface, the differential surface area, which has been already indicated as ds1. What is ds1? ds1 is actually, 1 minute, x is equal to 0 to 3, x is equal to 0 to 3, 3y plus z into the surfaces indicated by, we have seen it earlier, dx dz, and the direction is minus ay, dot product. ay can alone be equal to 1, isn't it? Ay dot ay can alone be equal to 1, though the vector is d is equal to 3x squared ax plus 3y plus z into ay plus 3z minus x into az. The vector has 3 components, but the surface area has got only one unit vector, ay. So ax with ay may be 0, and az with ay will also be 0. So definitely I have to work only with the, what is it? I'm going to just work only with the ay component alone. Then only this surface area is perpendicular to ay. So I take only the component related with ay alone. Magnitude along y-axis is alone taken into consideration for this dot product. Okay. So if you evaluate this, ay dot ay is equal to 1, you know that, and along this surface area y is equal to 0. So this integration will get reduced. Surface integral of d dot ds1 may be indicated as z is equal to 0 to 2, x is equal to 0 to 3, minus z dx dz, which is indicated as, when you integrate dx with respect to x, it gives you x, where the lower limit is 3, 0 and upper limit is 3, and when you take ez, obviously minus z squared by 2 will be the result of integration. The lower limit is 0, upper limit is 3. So obviously when you substitute all these values, this becomes simply 6. So please do remember, surface integral of d dot ds1 will be equal to minus 6. Keep it in memory. We may have to refer to it later. This can be on one side. Similarly, if you calculate surface integral of d dot ds2 over the second surface, Where is it located in the diagram? It is seen as the surface available over the space situated at the back side, isn't it? So d dot ds2 will be equal to z is equal to 0 to 2 and y limit is 0 to 3. So 3 minus 3x squared dy which is equal to minus 3 of course can be taken outside, and you know that for this surface x is equal to 0. So when we substitute whatever may be the integral 0 to 2 and y is equal to 0 to 3, when you substitute x is 0, the integration will become completely 0. Okay. Similarly, when you ask me to find out the surface integral of d dot ds over third surface, you will notice that the result of this integration will be over the curved surface. So phi is 0 to pi by 2. I have to take the radial component, and of course r d phi dz will be taken into consideration, because then only the ar dot ar radial component versus radial component will be equal to 1. And I have already told you the radius of the cylinder is 3. All these parameters you have to keep in memory. How to obtain the dr component? Now, cylinder. To find dr component, d vector is taken and it is projected on ar unit vector, because converting vector d to a cylindrical system for the purpose of finding out the magnitude of dr, d dot ar. So 3x squared ax dot ar, right? Similarly 3y plus z ay dot ar. You know what is d vector? Plus 3z minus x is the component magnitude of this vector d along z axis. So az dot ar. I've given all these things. Now you can find out that before moving further, you have to take the conversion parameters also. X is to be converted as r cos phi, y is to be taken as r sin phi, because when you convert from Cartesian to cylindrical, such transformation formula must also be used. Then only the result will become d dot ar, which gives you dr component 3r squared cos squared or cos cube phi plus 3r sin phi plus z. Into, of course, you have to replace y by r sin phi. With r is equal to 3, you can notice that the integral z is equal to 0 to 3, y is equal to 0 to, z is equal to 0 to 2, y is equal to 0 to 3, dr r d phi dz now can be written as d dot ar. Already I have told you r is equal to 3. So 3 into r squared, 3 squared. So it becomes 3 cube, double integral. One is with respect to z is equal to 0 to 2, y is equal to 0 to 3. And you can notice that it is 3 cube cos squared. Is it cos squared or cos cube? I'm sorry, cos cube phi plus 9 sin squared phi plus ez sin phi into r is 3, so r d phi dz. This expression is furthermore reduced. Surface integral of d dot ds3 will become the surface integral. I'll keep this integration from 0 to pi by 2 for the purpose of simplifying it later. Whereas we have, when you multiply it with the first component, 3 power 4 cos cube phi, and with respect to z, if it is integrated, it becomes dz z 0 to 2 is are the limits, and 27 9 into 3 27 sin squared phi multiplied by integration of z dz z, lower limit is 0 and upper limit is 2, and plus 3 sin phi. Okay, lower limit is for the z component 0 and upper limit is 2. So the entire the expression is to be now integrated with respect to phi. Now you can notice that the integral becomes 0 to pi by 2, 162 cos cube phi plus 54 sine squared phi plus 6 sine phi multiplied by d phi. So I should know the trigonometric identities. Cos cube phi will be replaced by 3 cos phi plus cos 3 phi divided by 4, and sine squared phi will be equal to 1 minus cos 2 phi divided by 4. And if you start solving the expression, surface integral of d dot ds3 will become simply integration phi 0 to pi by 2 and 162 cos cube phi can be replaced by 3 cos phi plus cos 3 phi divided by 4, yes, plus the next component 54 sine squared phi, which will be equal to 1 minus cos 2 phi divided by 2 plus 6 sine phi. The entire expression is to be integrated with respect to phi. When you solve it, it becomes 156.406. So how many surfaces we have completed? Over first surface ds1, second surface ds2, third surface ds3. Now we move on to the fourth surface. In the fourth surface, I'm sure the z value will be equal to 2. So surface integral of d dot ds4 will be equal to r varies from 0 to 3 and phi varies from 0 to pi by 2. The expression will be only the fourth surface. Do you know where is it located? Do you remember? I think you would have noted down fourth surface. Can you identify where is the fourth surface? The fourth surface is at the topmost part of the cylinder, which is cut by z is equal to 2. So you will automatically find out this expression will become r is equal to 0 to 3 is about radius, whereas phi, the curve, will be limited by 0 to pi by 2, right? So automatically this expression becomes d dot ds4, which is equal to 3z minus x multiplied by r d phi dr. Okay, and we have to again make use of the conversion Cartesian to cylinder, where x is equal to r cos phi and z is equal to 2. When you use that, the x is equal to r cos phi and z is equal to 2. So the first value will become 6. The second value will become, yes, r cos phi. So already you have r d phi, r cos phi, r d phi, multiply, you will find out the product will become. So let me evaluate this. D dot ds4 over the fourth surface will be equal to r varies from 0 to 3 and phi varies from 0 to pi by 2. The expression will become 3z. So this is simply, z is 2. So 3z, 6 minus x is r cos phi. So let me substitute r cos phi here, r d phi dr, right? So the lower limit will become, multiply and expand. You can find out that the first component will become r is equal to 0 to 3. The second integration will be over phi is equal to 0 to pi by 2, 6r. The second one will be r squared cos phi. Simply r is alone multiplied, r squared cos phi d phi dr. Evaluate this. Surface integral of d dot ds 4 will be integral from phi is equal to 0 to pi by 2. The first one is 6r dr integrated. So 6r squared by 2 minus the second component is r squared cos phi. When it is integrated with respect to r, cos phi is treated as constant, r cube by 3 into cos phi, where the lower limit is 0, the upper limit is 3, and again this is to be integrated with respect to phi. Now you can find out that this becomes phi is equal to 0 to pi by 2. Yes, 27 minus 9 cos phi, yes, into d phi, which will be equal to 27 into d phi will be phi, so 0 to pi by 2. The second component, 9 is taken as a constant, cos phi, when it is integrated it gives me sin phi, lower limit is 0, upper limit is pi by 2. As you all know, when you complete this evaluation, this will result in 33.411, for example. How many surfaces are yet to be completed? The evaluation of this expression d dot ds over the last surface So where the surface will be equal to, but the surface is determined from, where is that surface? At the bottom of the cylinder. For this ds5, z is equal to 0. Everybody knows. So surface integral of d dot ds5 will be equal to r is equal to 0 to 3, phi is equal to 0 to pi by 2. And you can see that only the component which can help you to find out the minus r d phi dr, r d phi dr will be equal to, as I have already known, x is equal to r cos phi is a suitable replacement for conversion of Cartesian coordinate parameters into cylindrical coordinate parameters. So when I consider the lower limit is 0 and upper limit is 3 and lower limit is 0 and upper limit is pi by 2, the value will become r squared cos phi is r squared cos phi dr d phi, which will be given by phi is equal to 0 to pi by 2 r cube by 3 cos phi, lower limit is 0, upper limit is 3 d phi. So you can notice that r cube by 3, r cube 3 cube by 3, 27 by 3, 9. Whereas cos phi, when it is integrated sin phi, yes, cos phi, when it is integrated sin phi, lower limit is sin phi, lower limit is 0 and upper limit is pi by 2. When you substitute this value, this becomes simply 9. So what are all the surfaces you have taken into consideration? D dot ds is considered to be divided by the first surface, it is minus 6, the second surface it is 0, the third surface it is 156.406, the fourth surface it is 33.411, or fifth surface it is 9, so totally it becomes 192.817. So this is the result of left hand side, right? LHS. In the divergence theorem, the right hand side is provided by RHS. What is right hand side? Volume integration of del dot D into dV. Okay, what is del dot D? Del dot D will be equal to dou by dou x dx plus dou by dou y dy plus dou by dou z dz. So this is equal to 6x plus 3 plus 3, which is given by 6x plus 3 when we integrate it, because for the computation of volume integral of del dot d dv, we need to obviously look into z is equal to 0 to 2, and phi is equal to 0 to pi by 2, and for r is equal to 0 to 3. Yes, 6 x is replaced by r cos phi plus 6, whereas for the volume, in the case of a cylinder, differential volume is given by dr r d phi dz. So r dr d phi dz. Substitute it, you will automatically find out that this is equal to z is equal to 0 to 2, phi is equal to 0 to pi by 2, and r is equal to 0 to 3. The expression will become simply reduced in the form of, we can complete, r can be taken inside, so 6r squared cos phi. The second term will become 6r squared, yes, dr d phi dz will alone be available. With respect to r once it is integrated, with respect to d phi once it is integrated, there are two summations, so kindly look into it and complete it accordingly. So the volume integration will become, for the purpose of clarity, I can do it like this. Phi can be integrated, z can be integrated, lower limit is 0, upper limit is 2, and with respect to r, if it is integrated, 6r squared will become 6r cubed by 3 cos phi. As far as the integration with respect to r is concerned, cos phi will be treated as a constant. And the next one is 6r squared by 2, lower limit is r is equal to 0 and upper limit is 3. So the integration yet to be completed is only over phi is equal to 0 to pi by 2. So the value will be equal to 2 into integral phi is equal to 0 to pi by 2. So the entire integration will become 54 cos phi is plus 27 multiplied by d phi, which is equal to 108 multiplied by sin phi. Lower limit is 0 and upper limit is pi by 2. And if you look at the second component, it is 54, where according to the d phi, if it is integrated, phi will be the answer, lower limit is 0 and upper limit is 0 to pi by 2. The answer will be equal to 108 plus 54 multiplied by pi by 2, which is equal to 192.82. Yes, divergence theorem is verified. Why this took this much lengthy computation? Because the diagram What was given for analysis is a wedge portion, cut and removed portion from a cylinder. Unfortunately, when it is cut from a cylinder, obviously they start with x is equal to 0 and y is equal to 0 plane. Yes, y is equal to 0 plane, and they have used z is equal to 0 and of course z is equal to 2. All those knives, the planes, were used to cut and remove the cylinder part. So there are 5 phases. One is over the left side, the other is over the back side of the cylinder, the third portion is over the curved part of the cylinder, and the fourth one is at the top part of the cylinder, where the fifth one is defined over, where is it available? At the bottom of the cylinder. So left curved portion, left back side curved portion, bottom and the top planes. That's why we need to work with 5 different surface integrations, and in all those 5 surface integrations, ds part will vary and d dot ds is to be separately computed. In some of the computations, we could not keep Cartesian coordinate system components as Cartesian coordinate system components because some of them require cylindrical evaluation also. Over all the 5 surfaces, when we compute and accumulate the result, only left hand side part was obtained. As far as the divergence theorem is concerned, it includes the divergence of d over the volume, differential volume specified in the cylinder. So obviously del dot d needs to be computed, and then and there we need to change x, y components into phi and r components. Thank you so much.